Hello everybody, this is Toby Delbrook, Institute of Neuroinformatics, again representing us and also Innovation Labs. In this video tutorial I'm going to show you how to use some of the hardware controls for some of the cameras. I'll run the latest development branch of jAER from the NetBeans development environment here. And I have two cameras plugged in, a DVS128 and a DVS240C, plugged into different USB interfaces. Now when I launch the viewer, it'll always come up with the last configuration, which was set up for DVS128. I'll see that it doesn't actually start showing live output. The reason is you have multiple cameras plugged in here, multiple devices, could be silicon retinas or cochleas, and so you need to select which hardware interface is associated with this particular AE chip, in this case DVS128. If I unplug the DVS240C, which I'm going to do right now, it'll immediately open the single device, which is DVS128, which you see it running here. Let's go to normal rendering mode by pushing C to change the color mode. And now you see the scene here in my office with Hakeem Olajuwon cut out, myself, and the bookshelves and so on. So what I'm going to show you now is how to use some of the hardware controls to control the biases of this DVS128, and then later I'll show you the more advanced controls or much fancier controls to control the DVS. So if you go and click on this hardware configuration button, it opens the hardware control panel, which opens in different modes: expert controls, which allow you to control the individual biases of the bias current generator on the chip, or in this basic controls, which encapsulates these controls into a simplified user view. You'll see here that in this view you have a bandwidth control, which tweaks the bandwidth of the pixel front end, the photoreceptor. There's a threshold control that controls the event threshold. There's a maximum firing rate that controls the refractory period of the pixels. And there's an on-off balance that controls the balance between on and off events. So for the rest of this, I'll just switch to this red-green view that shows the on events in green and the off events in red. Here you can see my finger is darker than the wall back there. So the leading edge of my finger is red and the trailing edge is green. Does that make sense? Remember, you can always listen to the spikes if you right click on a pixel. I'm not sure if you hear the click sounds. It might not be recorded here, but if you right click on a pixel, you can now listen to the spikes from that pixel. So what I'm going to do here to demonstrate these controls is to use a stimulus, which is a rotating fast dot. This is a disc, a white disc, sitting on a SpongeBob fan, which used to be a SpongeBob fan. When I push the button on the bottom of this guy here, the disc starts rotating and it generates a very fast stimulus. I'll open the lens wide open here to start out the tutorial. And now you see that even when the disk is spinning very, very fast, probably a couple of hundred hertz, it still sees this dot. To better expose that, I'll go to red-green view. And now when I turn on the disk and start spinning it, you see that it's responding to this black dot. This little black dot on a white disk, the leading edge of the dot is red because the pixels are getting darker, and the trailing edge of the dot, which you should see there, is green. The leading edge is red and the trailing edge is green because at the trailing edge the pixels are getting whiter. So that makes on events. So to show you how this hardware control panel works in the simplified user view, I'll select the bandwidth button, the bandwidth slider here, and slide it around. You'll notice that if I just slide this around, the only obvious effect normally is that perhaps the sensor gets a little bit less noisy. Let's see whether any filters are enabled. We'll turn off this existing filter. Yeah, we see that no filters are enabled, so we're just seeing the raw data from the sensor now. How can I see that no filters are enabled? Because none of these checkboxes are enabled here. That's because we want to look at just raw sensor data. So the effect of changing the bandwidth for normal situations is not very dramatic. If I increase the bandwidth a lot, from all the way from slowest to fastest, all I do is get a bit more noise. Of course, if I increase the pixel bandwidth, I'm going to introduce more noise because I'm integrating over a shorter period of time, and then the photon shot noise is going to be bigger. and so that generates more noise events. So if I go back to the nominal settings and show it the dot here, what I should see is a kind of a mixture of red and green, or kind of yellow. You see it's dominated right now by red. It means it's dominated by off events, which indicates that it's responding mostly to the leading edge of this black dot. I can try to use this on-off balance here to slide it more towards on events. And if I do that, you notice it turns green, so that you get more on events. Or if I slide it this way, it turns red, and you get mostly off events. So it's kind of balanced. But this does suggest that perhaps the bandwidth is a little bit too low of the pixel. So let's increase the bandwidth of the pixel, and hopefully we'll get a better mixture of red and green. Well, it's not obvious here, so let's adjust the slider again. And maybe we can get it closer to a mixture of red and green. Okay, so now you see what's happening. If you adjust these sliders too far out of the nominal range, then the sensor just stops working. But that's the situation right now. We kind of have a dominance of red off events. If I slow it down a bit, you should start seeing more of a mixture of red and green events. All right. So let's see what happens if I reduce the bandwidth a lot. If I reduce the bandwidth a lot, you should see eventually this dot disappear, because the pixels are simply not fast enough to see the dot moving. That's not the case here, even though we're only using fluorescent indoor illumination, because the pixels are just too fast. However, if I now take the aperture and close it down a bit to make the sensor darker, so now we see that the pixel under normal stimulus still sees fine, but if I show it something really fast moving, it just doesn't see it. You see how this dot kind of disappears. I can now rescue the situation if I increase the bandwidth again using the slider. I'll just slide it over to normal bandwidth or to high bandwidth. And now if I go to really high bandwidth, you see the dot come back. In fact, now let's make a little recording of this to show you how you can do that and inspect high-speed stimuli. So I'll record for a moment, and then I'll stop recording. I'll save this file. You notice that it's time-stamped with the name of the chip and the date that it's recorded, the serial number of the camera, and maybe this is the device ID if you have multiple cameras plugged in. So I'll save this here in my DVS128 folder. I'll give it a name here, dot spinning. And now if I play back this data, I should see the spinning dot. Now, it's not very interesting if you just play it back in real time, but if you slow it down a lot using the S button, you see, so we're only playing 65 microseconds per rendered frame. You see that in this situation, the sensor is really only responding to the leading edge. The pixels don't have time to recover, and so the response to the trailing edge of the dot is kind of blurred out. That's typical for these sensors because of the dynamics of the pixel. So let's go back to live data again. Now, if you showing in full contrast under this high bandwidth situation, you get quite a bit of background activity. You notice that it consists almost entirely of on activity. That's because of the leakage, junction leakage, and the reset switch in the pixel that tends to make a fictitious constant increase in pixel brightness that generates this background activity. If you want to filter that out, as shown in different tutorial, you can simply turn on this background activity filter and set the time constant of that to some short time constant, say 10 milliseconds, this correlation time, and that'll get rid of almost all the background activity, especially when you have a moving stimulus. But let's turn that off now because we're interested in the raw sensor performance. If I go back here to the hardware control panel and set ourselves back to nominal bandwidth, which, by the way, we've gotten to by loading a set of biases. So if I go here and say load settings in this hardware control panel, I can go and load settings, and when I navigate then to the jAER folder, bias gen settings, and find the folder for the particular camera, which should be DVS128, you'll come to a set of standard settings, fast, slow, and others that are not so useful. These are just nominal bias current settings that get the camera working in some state. So let's load the DVS128 fast again. And that will reset the bias currents in this expert controls to particular sets of currents. For instance, the photoreceptor bias is set to 1 nanoamp or 900 picoamps. the differencing amplifier is set to 60 nanoamps. The on threshold is set higher to 900 nanoamps, and the off threshold here is set lower to about 600 picoamps. Notice how the on threshold is higher than the differentiator and the off threshold is lower than the differentiator. Basically, the distance of these thresholds, these two thresholds here, to the differentiator set the threshold of the pixel for making events. So you can go, with some experience, you can go and manually adjust these settings. If you slide them all to the right, everything will speed up in the differentiator stage. If you slide them to the left, everything will slow down. These other biases have to do with other things in the pixel, like the refractory period, the pull-ups on the X and Y arbiters, request lines, and so on. These are kind of specialized settings that you have to know how the pixel architecture and the pixel circuit to make sense of. If we go back to the basic controls again, another thing you can do is adjust the event threshold. Let's go to a lower contrast viewing mode and go back to the normal view in grayscale and see what the effect of this event threshold contrast is. You'll notice if I slide it to the right, you should get a slight decrease, in the amount of events. So I'll hold it there. If you set it too far, you see the sensor stops working. It really is a nominal range over which everything still works. Now you should get less events. You see how it's a bit dimmer. And if I slide it to the left, I decrease the threshold. If I slide it too far, it just stops working. But I can slide it a bit to the left, and I should get a lot more events. So you can play with that a bit to reduce the threshold to make events, or increase the threshold to get less events if you're running out of bandwidth. Another thing you can do is set the refractory period. That's the time that the pixel ignores its input every time it sends an event. Best way to demonstrate that is to use a filter, like the info filter, to show the event rate as a function of time. Generate a stimulus, like the spinning dot. I'll open up the lens again so that we get lots of events. Let's just get it in focus here. Now I'll reset this info filter. I'll start the dot spinning, and you see as the dot starts spinning, the event rate goes higher and higher. And now you can read on this scale here the rate of off events and I think on events. I'm not sure which is which here, but it shows the event rate in hertz or kilohertz. It also shows the number of DVS events. There's a bug here that doesn't actually show the on and off events count separately. We can go and adjust this stuff here and turn off some of the statistics here, I think. If I go and play with this stuff, I can get rid of that display. Anyway, I'm interested in the rate trace here and these event rate bars here. I'll set the scale of the event rate bar higher so that it gets in range. And now what I'm going to do is go mess with the refractory period. If I decrease the refractory period, so increase the maximum event rate, it doesn't have much effect. In fact, the sensor stops working after a while. If I increase the refractory period, it should have an effect and limit the maximum event rate. Yeah, you see here, if I really decrease this a lot, it decreases the event rate from the nominal rate of like 700 kilohertz down to about 50 kilohertz. So you can have fun, make some recordings, and see what the effect is on high-speed motion of this refractory period. Another thing you can do with this is try to balance the on and off event rate for a particular input. So take this same spinning dot as an example, and now look at this on and off event rate here at the top. What we're going to do now is change this balance, try to change this balance here to get it more balanced, a little more balanced. Okay, so if I turn it a little bit to the left, you see the sensor is actually limited in bandwidth. You see this is a typical effect if you go to too high bandwidth, it starts scanning itself. But by sliding a little bit to the left, we've balanced the on and off event rate. If I slide it back to the nominal settings, you see it's dominated by the bottom event rate. If I slide it more to the right, even more of that type of event. So that concludes this basic demonstration of how to control biases on a DVS128. Thank you for your attention.